Yeah, what we're going to do in this course, we're going to study geometry of curves and surfaces, okay, and how to describe the curvature of a curve and a surface, okay, and how to express a curve or how to express a surface in the space, okay, and this is very important. To learn how to describe the surfaces. If you took a multivariable calculus, you already learned something, okay? But we're going to go beyond that, okay? So, so let's see. So n-dimensional, three-dimensional space, right? We just draw. Okay, let me draw this. Okay, three-dimensional space. You have to draw x, y, z coordinate system, okay? And high dimensional space is very hard and difficult, very difficult to draw. Okay, so if it's two-dimensional, that's just R2. Okay, with a coordinate system. Okay, a curve in the space, a curve in the plane. How can we study it? Okay, using calculus, right? When you see a curve like that, it's there. How can I study it? Using calculus. Okay, the idea, yeah, this is a curve C. Okay. This can be a parabola and could be determined by some equations, okay, algebra equations. So in order to describe it, I have to find a map, okay? I have to find a map. This is a curve C. I don't even mention in which dimension, okay? But we as a human being can only see a curve in 2 or 3 dimension space. We are not able to see a curve in high dimension space or imagine. It's very difficult. Okay? So a map, okay, this is A and B, okay? So in order to understand this curve, I have to find a map. Okay, this is called gamma, okay? Such that, such that C is going to be the image of gamma. So that means gamma and the B, okay? That's the image, okay? You send the interval onto the curve, okay? In this case, we said that gamma is a parametrization of C, okay? Right, once you find the one, it's parameter of C. And gamma itself is also called parameterized curve. Gamma itself, it's a map. Okay? It's not like a curve. When we talk about curve, we always see a curve in the space already. So gamma is also called a parameterized curve. Okay, it's actually a map. It's not, when we say use the word curve, we mean an object, okay, one-dimensional object in space. Now, actually here the map is also called a parametric curve, okay? More precise should be a parameterized map for a curve, okay? That's not a big deal. All right, so let's take a look at example, okay? Example. Yeah, let's take a look at the example. Okay. C is in C is in R2, determined by, given by y equals x squared. Okay, y equals x squared is a parabola, right? The graph of y equals x squared is a parabola, okay? And it's curve, right? Parabola is a special curve. It is a parabola. Okay. Right, so it's a curve. It's a curve in R2. The parabola is a curve on 2. Now, let's try to find a parametrization for this curve, okay? Which is a map, okay, which is a map from let's use one parameter, so from R, right, on to here, okay? How can I find this map? Okay, if this is a T And here's a point x and y. I just need to find x and y, right? X and y are function of t. Right. One choice is gamma t is going to be t and t squared. T is between negative infinity, positive infinity. Right. Right. So this is indeed a parametrization. It's very natural, right, of this parabola. Right. When t runs from negative infinity to positive infinity, you get a curve. You get a parabola in the xy plane. Right. But this is not unique parametrization. There's another. So parametrization is not unique. This is another one. Is going to be t cubed t to the power 6. This is also gives you a parametrization. So parametrization for a curve is not unique. This is just a simple example, right? Yeah. Why t cubed t? You can see that t cubed. Yeah. When t approaches negative infinity, t cubed approaches negative infinity, and t to the 6th power approaches positive infinity. So you will get the same image, okay? So both gamma and gamma tilde have the same image, right? Same image in R2, okay? So that same image is a parabola. Okay, that's a good example, right? Yeah, the relationship, if this is x, this is y, right? You can write it like that, x equals t and y equals t squared. So y is going to be x squared, right? The t is equal to x. So that's why this is implies y equals x squared. So at least you can see that the image is going to be the parabola, okay? It's a part of the parabola. And this also implies that y equals x squared, right? Y equals x squared. Okay, so that's the reason the image of those two parameters curve in R2, there's a portion of they're going to be the portion of the parabola, but actually they occupy the whole parabola. All right. Now sometimes different parameterization only can cover a portion of the curve. Okay, so how about to see it's a circle with a radius r squared. Okay, r is a positive number. Okay, so it's a parabola. It's a circle with radius r. Now, question is how do you describe? Can we find parameterization? I think somehow we can find parameterization, but the parameterization is not going to be one-to-one because we have this is a strict line, right? And you want to have a map. You cannot map the whole line one-to-one to a circle. That's topologically they're different, right? Yeah, this is a gamma. Okay, let's do our best to try to see it. Okay, my first one, gamma t is going to be t and the square root of r squared minus t squared. Okay, t is going to be negative y to the positive r, right? So here 0, negative r, positive r, right? Right. And this is the curve you're going to get. Okay, so what that tells you, you do find the parametrization. Yeah, how did I get this? First of all, question, right? How did I get it? Well, I get it in the following way. X squared plus y squared equals r squared. So y squared equals plus minus a y. It's corresponds to r squared minus x squared. Okay, so y equals that. So if x equals t, y must be square root of r squared minus t squared, right? So if x equals t, then y equals plus minus r squared minus t squared. Now, if you choose a positive, then the image is going to be the up semicircle. If you choose a negative, then the image is going to be the lower semicircle. Okay, lower semicircle, right? So it has a positive case. Yeah, the image will be the up semicircle. Okay, so this is the y part. Yeah, so image for gamma is up semicircle. Okay. Now, is there any other natural parametrization? Yeah, we can find another one. Because x squared plus y squared equals r squared, right? We also know that cosine squared t, sorry. Yeah, we also know that r cosine t squared plus r sine t squared equals r squared. So it's natural to write, yeah, so you can get x to be r cosine t, y to be r sine t, okay? Right? Then x squared plus y squared is going to be r squared. Okay. So we can construct another one. Let's use a different notation. And this is going to be r cosine t, r sine t. Okay. There's no restriction on t. All right. So what do we get? Let's understand this parametrization. Okay. So this is a whole line. Okay. It's t, right? Here's a circle. Okay. When t starts from 0, where it is, it's going to be here. Okay. When t increases, this is image, right? Yeah, you imagine it's moving, you know. Okay. When t increases, you get some point here. Okay. And clearly, when t increases from here to here, then you get from this side to this side rotate. Okay, and this will be pi. And you can continue, right? And continue. Then it's be 2 pi. So you don't need the whole line. Okay, the image of gamma tilde from interval from 0 to 2 pi is the circle. Okay, I do not include 2 pi. If it's 2 pi, that coincide, you know, there's overlap. Yeah. Okay, it's a whole circle, right? The good part of this is I get a parametrization to cover the whole circle. The one above one is only covers the semicircle. It involves the square root. So here you have sine cosine, does not involve square root. Okay. So there are multiple parametrizations for the same object, or for the portion of the object. Okay. Okay, so let's take a look at the next problem. Okay, let gamma t cosine 32 sine 3t, right? T is a whole line. Yeah, can we describe the image? In lot 2. Right, so sine cube and t is defined, right? It's defined for all the t. Right? It's similar to the circle. Okay, when t equals 0, it's here. When t equals pi over 2, it's here. When t equals pi, it's here. When t equals negative, when t equals pi 3 pi over 2. Right? T equals 0, t equals pi over 2, t equals pi, t equals 3 pi over 2. Okay. Okay. So so how can I connect them? I only choose a 3 point. I only choose a 3 points. Okay. 4 points, right? So actually when I connect them, it goes like that. Okay. So it behaves like a circle, but there's a cusp there. Right? And then you rotate it periodically, you know, when t increases. This is a t from, yeah, this is the image of the gamma and over the interval from t from 0 to 2 pi. Okay? And then it's overlap, you know, if t continually increases. Okay. Right, now I can describe this image using another equation. Since x is going to be cosine cube t, y equals sine cube t, right? I can then x to the 1/3 equals cosine t, y to the 1/3 is sine t, right? So therefore, I get 2/3 plus y 2/3 equals cosine squared t, sine squared t equals 1. Okay, so the image of the gamma is going to be the curve determined by this equation. Okay, right? So the image of gamma is going to be the graph of this equation. Okay. But you can also change the parameterization. Okay, then so that means this graph, if then gamma is a parameterization of this graph, right? But then there should be, you know, you can also find other parameterization. Okay. Well, so let's go to the general case. Okay, so this is a curve C. Okay, and here's the map. Okay, this is arbitrary point x and y, or even more variables. Okay, and this is t. How to determine a tangent? How to determine a tangent line? Right. how to determine the tangent line? I assume that gamma, which is t, x t, y t, is differentiable. If you differentiable many times, then we say it's smooth, okay? Right. I'm trying to find a way to determine the tangent line. So what I'm going to do is that look at t plus delta t, and somewhere here. So here's gamma t, right? Here's gamma t plus delta t. So this will be the how to define the tangent vector, right? Then you can determine. Yeah. So the difference, right, is the vector, this vector. But this vector is getting shorter and shorter. Okay, when delta t approaches 0. So I normalize it, kind of normalization. I divide it by delta t. Right? So let's consider, so this is going to be the normalized of this, maybe it's longer like this to the point here, right? Yeah, the delta t could be very small. Right. So anyway, it's in the same direction as the vector. We call it secant vector, maybe, right? So this one has a limit as delta t approaches 0. It's gamma prime t. So gamma prime t should be viewed as tangent vector. All right, so this limit can be viewed as vector tangent to the curve. It's as though this at the point is gamma. Okay. Okay, so this, y, when you say y, the derivative is going to be it's called a tangent vector. Okay. Because the derivative comes from this ratio. This ratio determines the vector. They're almost tangent to that point. Okay, then you take the limit, you get derivative. All right, so this is the idea why gamma prime t is called a tangent vector. Okay. Okay. Let's take a look at some examples. Okay. Okay. Assuming that the tangent vector of a parameterized curve is a constant vector. Then then what do you get? Think about, right? So gamma is a parameterization of the curve. So gamma prime t equals a constant vector. Okay. So what you can get from here? Well, you can solve it, right? You integrate it, gamma must be equal to at plus b. Okay. All right. So this is a parameterization of a straight line. Okay. This is a parameterization of a strict line. All right, once we get the concept of the tangent vector, and we try to derive the formula for the length of the curve. Right? Let's try it. This is a curve, right? We assume that it's the image of the parametrization, smooth parametrization. Okay, assume that C is the image of a smooth parametrization of C. Okay. So gamma is going to be from A to B and on to C. Okay. So how can I measure the curve in the space? Okay. Well, first of all, you try to find the parametrization, which covers the whole curve. Okay. And then we try to derive the formula. Okay. How do I do that? I partition the interval. This is a calculus idea, right? Okay. Then the length is almost equal to sigma n, I from 1 to n. The difference of Ti minus gamma Ti minus 1. Okay, so what you do is here, okay, this is a map, right? Here's Ti minus 1, Ti, and this will be gamma Ti minus 1. So draw the line, right? So the distance between those 2 points, I can call it Pi minus 1 Pi and P0, right? P1. So the distance between Ti minus 1 Pi is just the length of gamma I minus gamma Ti minus 1. Right? It's the difference of two vectors. So add them together, there will be total, right? So the length is going to be sum of this, right? Okay, I'm going to rewrite this by the mean variance theorem. It's going to be the derivative of some Ti star and the Ti plus Ti Okay. This is called the mean variance theorem or not, right? Yeah, the derivative times this. So you replace by the above expression. Right. So what is this? This, if you take the limit, It's nothing, but this integral. Okay. So we have the formula. The length of the curve C is just equal to the formula, equal to this integral by the formula. Okay. Okay, this is how do we derive the formula. Now we're going to use that to find the length of the curve. Okay. Right. So as long as you have a calculus idea, it's easy to derive the formula. All right, so let me take a look at the example. Okay. Gamma t is going to be cosine RT R sine t. Okay. And the t is between 0 and the 2 pi. So the image is a complete circle. Is a circle with the radius. Okay. So let's find the length using this parametrization. So what is the length of the curve, right? We can find out. Okay. Gamma prime is going to be negative R sine t, R cosine t. Okay, so the length is going to be square root of negative R sine t square, cosine square t square. So after simplifying, it's just R square. Sine square t plus cosine square t, and that's just equal to 1, then it's R. Okay, so the length of the tangent vector is constant length, is a constant. Right, so the total length of the circle C is being integrated from 0 to 2 pi, right? And this just equal to R, and that is 2 pi R. Right, so that is the length of the circle. You see, use the formula, it's very easy to find out. And this is a, let's find another parametrization. Right. I can find another parametrization. Gamma t. Okay, I'm using, it's still R, cosine, but t will divide by R. And this time, in order to get this whole circle, t is between 0 and 2 pi R. Okay. Okay, So let's check, right? Find the derivative. I'm going to use this one. The image is the same image, right? Yeah. This is going to be just negative sine RT because R cancels out. That's going to be cosine T of R. So the length is going to be just 1. Right, which is just equal to 1. All right, so then the length of the circle is going to be integral from 0 to 2 pi r. And because it's 1, so it's going to be 2 pi r 1 dt, which is 2 pi r, okay? Yeah, think about that. Now, why there's you see, you end up with the same length, right? 2 pi r. So it doesn't matter the parametrization. You should be able to get same length. Right? Otherwise, it's the wrong formula, right? And if we derive the formula using above ideas, and the length of the curve should be independent of the choice of a particular parametrization. Yeah, you can look at this example using 3 parametrizations. There are other parametrizations, I know, but this is 2 of very natural. All right. So I'm going to introduce a definition. A definition, okay, gamma is said to be a constant speeding curve. Constant speed parameterized curve. Okay, this curve is actually just a map, okay? It's not like the object, it's curve. Okay, if equals constant, okay, the length. So that means the tangent vector is a constant length. Okay. Right. And gamma is said to be regular if gamma probability never be 0, okay, for any t, okay, it's regular. Right, so all our parametrization has smooth, okay, and then we're going to talk about reparametrization. I already said that some curve you can have 2 parametrizations, okay, so 2 parametrizations. Okay, so here they are related, right? So given a curve, a parameterized curve, parameterized curve, okay? Right, then if another parametrization, okay, gamma tilde, okay, is called a reparametrization. Of this given gamma. Right? If think about the distribution is very simple. This is C, right? So this is a gamma already. Okay, here's from A alpha and beta. Another parametrization called alpha tilde, beta tilde. Okay, this is a gamma tilde. Okay, I prefer draw a picture so it's easy to understand. Okay, and then parametrization. So they have to have an image. Right. Right. So how can I do it? It's a it's one-to-one, right? It's kind of one-to-one. So this is a C, and for any T tilde, I go to here to point, and I can reverse this procedure and go to T. So actually we have a map here phi. Okay. So if the following condition satisfied, phi, right, from tilde beta tilde to alpha and beta. Okay. This is a smooth bijective map. It's on two smooth bijective map. Okay. Such that the inverse is also smooth. We always want to differentiate them. Okay, so this map is the inverse. Okay, so such that slow down a little bit. Such that gamma tilde T tilde equals gamma. Okay. All right. Yeah, from this picture, it's easy to see. You take a common point, okay? So T tilde map to here, then you have a gamma tilde T tilde, and that should be coincide with gamma T. So go back to T. So given T tilde, you get a T. Given T tilde, you get a T. So the relationship is T is given phi T tilde, okay? And conversely, if given T, then you go from T to the point on the curve, then you go back to the interval alpha beta, alpha tilde and beta tilde. So actually you define a bijective injective, but we have to assume that it's at smooth. Yeah, let's take a look at the example. The example was just to when is the reparametrization of other one. Okay. Okay. Gamma T equals example gamma T equals T and T squared. Okay. And the gamma T tilde T is going to be T tilde cube T tilde 6. Let's find the relation between T and T tilde because I have the same image. The image will be same. Okay. The image of gamma is going to be the image of of gamma tilde, which is also, this is going to be the parabola, right? Right. So how can I get a relation between T and T tilde, right? Look at the above picture here. We are going to have the same point. Let's just solve this. Right, so you can solve T equals T cubed, and that's it. All right, so this is our phi T tilde. Okay? The inverse. Okay, so this is our inverse. You just solve for this. It's going to be T to the 1/3, I think. Yes. Okay. Now, so this phi, okay, take a look at this phi. Okay, it's from negative infinity to positive infinity to negative infinity to positive infinity, right? Phi T tilde equals T tilde cube. This is a bi-injective, but however, the inverse is going to T to the 1/3, right? This is also, but this is not smooth when T equals 0. So phi, this is not smooth at T equals 0. So by definition, gamma tilde, by definition, gamma tilde is not a reparametrization. It's another parametrization, but it's not a reparametrization of the given one. Okay? By definition, gamma tilde is not a reparametrization of gamma, but it is another parametrization of the curve of the parabola. Right? So don't be confused. Okay. So that means gamma tilde is better parametrization. Honestly, it's better parametrization. Gamma is a good parametrization for the parabola. Okay. So two parametrization, maybe given two parameters for the same curve. What I want to say that one of them may be not necessarily a reparametrization of another one. They're totally different parametrizations for the same curve. Okay, maybe you can say they're not equivalent, yes. And this is a liquidity starting point. Okay, so how to find well, we can find a new parametrization. If I want to find a reparametrization of the gammas, all you need to do is just find the function, right? Yeah. Okay. Okay. So now we assume that gamma is a regular parametrization. parameterized curve. Yeah. So gamma is from A to B. Right, we assume that's regular, so that means gamma upon T is never be zero, okay? For all T. Okay, let's find out. Let's define. All right, so let's find this. All right, so this what you get. Well, this is a arc length, right? Starting from gamma A to gamma T. All right, so this meaning is clear, right? So let's take a look at the derivative. So this S is going to be function of T, right? Yeah, and S starts from 0 all the way to L. L is the length of this curve C. Okay, you see that the derivative S with respect to T is nothing but gamma T. Okay, this is always positive. Right, so this is an increasing function, right? It's just measure length. It's a geometry mean is very clear. This is gamma T, and here from here to here, it depends on the function T. It's the length. Okay. I can define new parameterization because this is a gamma, right? And from A to B, I can find a new parameterization from 0 to L. And the gamma tilde, S tilde. Gamma tilde, T tilde, yeah, T tilde. Okay. So how can I do? So that's how you can define. So T is going to be the length from gamma A, right, to gamma T. Yeah, define gamma by if T tilde equals ST. Okay. So we can in the very abstract way to define new parameterization, and I guarantee this is a reparameterization. Okay, gamma tilde is a reparameterization of gamma. Okay. And also it's very important is I'm going to look at the length, right? The length of the tangent vector. when you differentiate this, right, you will differentiate by the chain rule. You can also, yeah. But this is nothing but the tilde dt, right? Because t tilde equals st, right? So that's what we differentiate with respect to t. And differentiate with respect to t. Now you get this. This is by the channel is going to be 1. Okay. So if you use arc length to reparameterize the curve, then this parameterization has a unit speed. Okay. That's a unit speed. Is it easy to find the if arc length? Not easy, not always. Okay. Let's take a look at an example. Okay, here's the example. Okay, gamma t equals r cosine t, r sine t. Right. Let's find a reparameterization of gamma t, okay, such that all right. So how do you find it? All you have to do is just find the t tilde, right? It's integral from 0 to t. Okay. That gives you the arc length. Okay, the arc length from gamma A to, yeah, this A equals 0 to gamma t, okay? So theta is going to be 0 t, and it's going to be r squared, cosine squared t, r squared sine squared t dt. Right? Because gamma t is given, right? Just differentiate. So you will get r dt. So you get rt. So that's the relationship. T tilde is going to be rt, right? And remember, right? So gamma t is going to be r cosine t, r sine t. T is going to be t tilde of r. r cosine t tilde over r. Okay, so this is nothing but gamma t tilde. Okay, this. Yeah. Okay, but not always, it's easy to find an arc length and then use a new parameter. It's not, in general, it's not easy. Okay, this one it's okay. So this is it's a gamma tilde is a unit speed term. Okay, let's take a look at example gamma t. So let's take gamma parameter is going to be 2 cosine t sine t negative, right? And 2 sine t cosine t. So it's negative. It's negative sine 2t and sine 2t. Right, double check, right? 2 cosine t and then negative sine t and 3 sine t and cosine. Can you check that, right? So this is going to be what? Wow, surprise, it's a unit speed effect. Right. All right. It's hard to draw this picture. All right, let's try to. Right. When t equals 0, it's here, right? When t increases. Right, when t equals pi, the t is here. However, when t increases, the y value is always positive, cosine value is always positive. It's going up, then going down. Just repeat it. Yeah, but we can still find the length, right? I just want to find the length of this piece. Okay, the length of that piece. It's the integral from 0 to pi over 2. Okay. So it's pi over 2. That's not too bad. Yeah, we find it. Okay. There are some. I'm done with the 3 sections. Okay. Today is basically about curves, tangent line, tangent vector, the length of a curve. Okay. You will be given the homework assignment. I think I'm going to post on the web, Canvas. Okay. But today's homework, if you don't see it, it's going to be 1.15. Got the second one. It's 1.2.2. (1.3.2). Right, 3 problems. Now,